Hello, I'm Chinmay Tope, and this is my Physics 2212 Lab 2. To introduce why this lab was conducted, it's first important to mention how similar it is to Lab 1. Like Lab 1, this lab will focus on electric charge, electric force, the principle of superposition, and Newton's laws of motion. Something new from the previous lab that is now going to be introduced in this lab is distributed charge systems, as you will see in the future slides. Coulomb's law, the expression for Coulomb's law is displayed on the bottom left with an image displaying the principle of superposition on the right, where the electric field at any position is the net electric field at any position is the sum of electric fields around or at that system at that point. Excuse me. Continuing on the introduction of this lab will also involve the computational modeling of physical properties, including electric fields, force, and gravity. Likewise, we're going to be doing this modeling using glow script, where we will depict forces acting on multiple objects and be able to assess or predict their motion. Continuing on, the main purpose of this lab is to extend our learning from the previous lab to distributed charge systems. Likewise, this is also going to add some complexity to the previous model that we developed. Still, however, we're going to utilize Newton's second law to determine the electric charge and electric forces present on, now in this case, a distributed system, whereas the previous lab focused on a single individual system, a point system, basically in the form of a point charge, whereas in this case, we're going to be utilizing line charges. Again, the two expressions for Coulomb's law and superposition are displayed on the bottom of the screen. Continuing on from the previous findings of last lab, we were able to deduce that the tape had a charge of 6.44 times 10 to the negative 7 coulombs. This was assuming that each tape was acting as a point charge, or both tapes have the exact same charge, net charge. Likewise, we utilized the motionless system along with the mass to be able to deduce this charge with the math displayed below. This is the math that we utilized in the previous lab to determine the actual charge present on the tape when modeled as a point charge. This model did not factor in air resistance, distributed charges, or differing charges between the two interacting tapes. Our lab will still continue to make a few of these assumptions, those being that there will not be any air resistance in our model for this lab, as well as different charges for this different charges between the two tapes. So basically, we're going to assume still that the charges on the tapes are still identical and that there's no air resistance. However, we are going to utilize a distributed charge system, which should provide a little bit more accurate information. Continuing on to the computational modeling is displayed on the screen. From left to right, the leftmost image displays a few key constants as well as tape measurements that are important to actually utilize in order to determine the net forces and charges present in the system. The middle picture displays the definition or a function to develop a line charge, which there will be two of in this case because there are two tapes. Each in this case will be behaving as a charge, distributed system of charges present on an infinitesimally thick line. Continuing on to the rightmost image displays calculating the forces and electric field vectors present on the top tape by the bottom tape. There's going to be two main forces modeled here. There's going to be a gravitational force that's present on the top tape, as well as the net electric force present on the top tape as well. Likewise, there's also the sum of many different electrical fields along with the distributed charges on the top tape as well. The computational model results are displayed on the screen right here. The model reported actually a decrease in the magnitude of charge from the previous lab. Likewise, it also reported a decrease in the electric force present on the top tape. The previous lab reported a force of 7.5 newtons, whereas this lab reported a force of 1.85 times 10 to the negative 3 newtons. Likewise, a computational physical model is displayed on the right, with the orange arrows representing the electric fields. Continuing on to discuss these findings, there was a decrease in the net charge, and this likely stemmed from the distance between the two tapes that they were held at. In the previous lab, the tapes were held extremely close, and so treating each tape as a point charge only factored in the distance with one electric field expression. However, for this lab, assessing each tape as many charges basically allowed that distance to exponentiate and drastically reduce the total attraction between the two tapes, which therefore decreased the total force present on the top tape. Likewise, to continue on with some key assumptions for this lab, the charges on the top tape were only affected by interaction with charges on the bottom tape. This basically meant that there was we didn't model or assess any interaction between charges on the same tape, which in reality would also be occurring. Likewise, we also assumed that the tapes had equal charge, and that was actually also needed to make this lab possible. To answer some key questions, what if we modeled each of the tapes as a single point charge, like in the previous lab? The two values displayed underneath that question represent the change in electric charge, the net electric charge on the two tapes. On the two tapes, the first number represents the charge before, where we modeled each tape as a point charge, whereas in the newer model, modeling each tape as a line charge actually provided a decrease in the magnitude of charge. To answer the second question, why did these estimates differ? It's likely that they differ because of, like I mentioned, the quality, or the addition of distance into multiple charges present on the line tape model. When there's multiple charges present, the net electric field on each of those charges will be less because there's interaction between the charges from the interaction between other charges on that same charge. Likewise, it's probably closer to the actual real value because in actuality, when ripping the tapes off of the table, you're actually creating a distributed system of charges. And because the tape is a linear system, it's not an individual in a two-dimensional system. There's probably going to be many more charges present on it than just assuming that it can behave as a point charge. Anyways, that concludes this lab, and thank you.